So let's talk about saving operands on the stack using a variety of push type of instructions, and also restoring the operands from the stack using the pop instruction. So first of all, let's try this. If we want to preserve the value of a register on the stack, and the reason to do that is that perhaps you're doing some sort of computation and using your registers as temporary values for your parameters and your formulas, memory addresses of your variables and so forth. So of course you may run out of registers that you need to use, so you can temporarily preserve certain registers on the stack. So we can say push for instance, push EAX, right? So EAX is a register, and we can push it, and we can comment here that this instruction would preserve register EAX on the stack. Of course, this is kind of simplistic comment because it just kind of explains what this push instruction does. Normally, you probably just want to mention maybe the reason why you're preserving this register, or whatever, closer to your program logic. But here we're focusing on the idea of these types of instructions, so that's my comment: preserve register EAX on the stack. So what push instruction does is this. So remember, we have our stack, which is given to us, and we have this ESP register that is already configured, and we know that by the time we start running our procedure, we have already observed this situation and discussed it, that this stack segment that we have at the top of the stack contains the return address to the code that made a call into our main procedure. And so this is what ESP register is pointing to at this stage. And as soon as we say push, remember, these are low addresses right here, low memory addresses, where's still a lot of free space in the stack memory segment, and these are high memory addresses. So therefore, if we want to push another thing on the stack, what happens is that the CPU will first subtract the size of this element. This is 4-byte size register EAX. So the value of 4 will be subtracted from ESP, and so it will effectively move to this memory location in memory segment, and this is where EAX will be written. Of course, it's just the value that's stored inside this register is written here. The register remains as is, but its value, whatever contained in this register, is written here. So I will say EAX here just to display that it's a copy of the EAX value. Of course, EAX itself does not change. So, but before this happens, push first subtracts 4 bytes because it was pointing here originally, and now it's pointing to this location, and now we saved register EAX. So let's make this somewhat recognizable. Let's load this register with some sort of recognizable memory pattern, so we can say move into EAX 0. We can say AA, BB, CC, and DD, something like this. Okay, so this is just a hexadecimal, let's just make it uppercase, hexadecimal pattern that we can easily recognize if we look at the memory when we run this program. So yeah, because we would like to be able to see this when we're debugging our code. in addition to this, what we can do, there is another format of this instruction, push D pushes double word, and this is when we need to specify an immediate value. So let's say 5, okay? So this push an immediate value onto the stack. Right, so again, it's kind of silly comment, but that's the idea. That of course immediate value is stored in the instruction itself, and push D requires to specify what is the data type. And the reason for this is that on x86 architecture, you can save on the stack 16-bit values and 32-bit values. So when we run this in 32-bit mode, I recommend that you should not try any 16-bit values on the stack, only 32-bit values. And push, if I didn't type D like this, would attempt to push a 16-bit size value 5 on the stack. Push D makes it push double word. Okay, push double word like this is what you would use in 32-bit mode, x86, to save an immediate value on the stack. The same thing happens again. Step number 1, ESP is subtracted 4, because this will be a 4-byte size integer, and 5 is written to the memory pointed by register ESP. Okay, so then of course these are examples of this happening in 32-bit mode. What it shows us here is that if we are using 16-bit mode and we say push EAX, push AX, which is a lower half of the register EAX right here. So before the memory, the stack memory is used, stack pointer here is also shown a 16-bit mode SP stack pointer. So it doesn't matter, it's just like basically everything is 16-bit in this example. So it's pointing to a certain address in memory, right? And then of course, because the size of AX here is 2 bytes, the stack gets basically is the value, this memory address that's SP is pointing to, we subtract 2, and so we end up pointing over here. And the lowest byte of register AX, which is register AL, of course, right? So this is, we know this register as register AL, is written into the lower memory, right? And register AH, which is the higher part, AH is the higher part of AX, is written into the higher memory. So this is the copy of our register saved, and these are just bit patterns, 12 hexadecimal and 34 hexadecimal. So here these are the values written specifically into these memory locations.